Hello everyone, this is Monwar and I am presenting my project proposal for computer vision, supervised by Dr. Muhammad Ashraful Alam. Today I will be introducing LG VIT, the lesson guide cross attention vision transformer. My research focused on achieving unbiased classification of human dermatological diseases through structural contour guidance. Automated dermal- dermatological screening has massive potential for early disease triage, but current model fails to perform equitably across diverse patient demographics. We identified that standard networks suffer from shortcut learning, meaning they minimize training loss by memorizing ambient skin pigmentation and lighting artifacts rather than the actual morphology of the disease. To solve this, LGBit uses a dual-stream architecture that explicitly decouple high-frequency structural boundaries from low-frequency color distribution. Clinically, early identification of infectious rashes is critical. However, conditions like early-stage monkeypox, chickenpox, eczema, and contact dermatitis share a high visual overlap, often presenting as enthematous pupils. The computer vision bottleneck occurs because model tokenize images uniformly. On lighter skin, inflammation presents as distinct red erythema with high contrast, but on darker skin such as Fitzpatrick types V5 and 6, erythematous lesions appear hyperpigmented or violaceous, blending into background. Consequently, model relying on color suffers, sharp accuracy drops on darker cohorts. In synthesizing over 50 contemporary studies, we observed two distinct architectural eras, both with persistent flaws. The standard CNN baseline like ResNet 50 have a strong local feature extraction but lack global self-attention, leaving them highly vulnerable to localized shadow artifacts. Controversially, vision transformer and advanced hybrid baselines such as SwinVit and Convex successfully capture global dependencies. However, their single-stream processing still allow learnable attention head to drift heavily toward skin color rather than structural boundaries. This highlights our targeted research gap. We need a deterministic, non-learnable, indicative bias that isolated boundary geometry like ridges elevation changes entirely independently of chromatic variation. Our solution LGBT integrates a fixed second order Laplacian high frequency pipeline with transformer cross attention. This ensures the model cannot unlearn edge extraction to revert back to color-based shortcuts. Our methodology relies on a dual-stream tensor ingestion pipeline. Branch A is the RGB chromatic stream, preserving color intensity, texture, and global semantic context. Branch B is the structural gradient stream. Here is the input is converted and luminance and passes through a second-order discrete Laplacian differential operator implemented by a fixed 3 by 3 kernel. This branch suppressed uniform skin areas and highlights step intensity gradients like lesion border and scaling. Looking at the architectural blueprint, you can see how we decouple structure morphology from the RGB channels. The core design principle is the fixed Laplacian kernel provide an explicit non-learnable inductive bias. This guarantees that The morphological stream remains entirely invariant to ambient skin pigmentation. Rather than using simple concatenation, LGBit employs cross-attention to fuse these streams, the queries and projected from the RGB stream to retain chromatical identity, while the keys and the values are projected from the Laplacian structural stream. Effectively, the model queries and the structural edge map to assign a special importance, locking its attention onto lesion border. Furthermore, to handle diagnostic ambiguity for multiple expert annotator, we optimize the network using soft target cross entropy loss. To validate the architecture, we utilizing four diverse benchmark datasets. Our primary dataset are Google Skin, which contain over 10,000 real-world clinical images with multi-data, rather differential evaluation, and Monk skin tone metadata, and the HAM 10,000 dataset for common pigmented lesion. For secondary and specialized benchmark, we utilize Mpox Vision V2 and Skin 2025 to focus on viral condition with high interclass similarity across varied demographics. All input are standardized to a 224 by 224 resolution with standard ImageNet normalization. Our experimental matrix compares LGBit against vanilla bit base and convex base and swing base. Beyond standard global metrics accuracy and micro RCUC, with our most critical matrix is stratified fairness. We evaluate these by calculating the absolute difference in AUC between light tone and dark tones, where a lower delta indicates greater demographical equity. In conclusion, LGB demonstrates significant technical novelty by providing that injecting non-learnable edge filter into attention map resolve the shortcut learn dilemma without the need for massive demographical oversampling. Clinically, this provides a highly reliable foundation for edge deployable teledermatology that maintain diagnostic equity across all ethic groups. Our execution roadmap focuses on completing full-scale benchmark training and finalizing our party metrics for publication. Thank you for your time.